In the last episode, we introduced the concept of wave functions as vectors in an infinite dimensional Hilbert space. Today, we will delve into linear algebra and show how nearly all of non-relativistic quantum mechanics can be derived from 5 theorems of linear algebra and the postulates of quantum mechanics. We shall formulate our discussion of linear algebra in terms of operators and functions, noting that any function can be represented as a vector in an abstract Hilbert space, and the operators we will deal with can be represented as matrices in the same Hilbert space. We define an operator as a linear operator if and only if it satisfies the following two conditions, that is, the operator A operating on the sum of the functions phi and psi gives A operating on phi plus A operating on psi, and the operator A operating on some number C times psi gives C times A operating on psi. These two conditions can be combined into a single equation by writing A operating on B phi plus C psi, where B and C are two in general complex numbers, gives B times A operating on phi plus C times A operating on psi. A function psi is said to be normalized in some interval, say minus infinity to plus infinity, if the integral of psi star psi dx over this interval is equal to unity. We now introduce Dirac notation for the function psi as a column vector in what is called the Ket space. Its dual is the row vector in the bra space. The Ket space and the bra space are both abstract Hilbert spaces. So in Dirac notation, we can write the normalization condition as bra psi ket is equal to 1, where psi is interpreted as a vector in an abstract Hilbert space. Its norm is then said to be unity, and geometrically this means that the vector psi has unit length. Two functions psi and phi are said to be orthogonal to each other if the integral psi star phi dx or phi star psi dx is equal to 0. This is also written as in Dirac notation as bra phi psi ket is equal to 0. Geometrically, this means that the vectors psi and phi are perpendicular to each other. Bra phi psi ket is the projection of the state vector psi onto phi. A function psi is said to be an eigenfunction of an operator A if the operator A operating on the function psi gives some number small a times the same function psi. The number a is called the eigenvalue of the operator A corresponding to the function psi. For example, e to the power alpha x is an eigenfunction of the operator d by dx with eigenvalue alpha, since d by dx operating on e to the power alpha x gives alpha times e to the power alpha x. Is e to the power alpha x squared an eigenfunction of d by dx? Let's work it out. D by dx operating on e to the power alpha x squared is equal to 2 alpha x times e to the power alpha x squared, which is not a number times e to the power alpha x squared, since 2 alpha x is a function and not just a number. So no, e to the power alpha x squared is not an eigenfunction of d by dx. Is cos alpha x an eigenfunction of d by dx? D by dx operating on cos alpha x gives minus alpha times sine alpha x, which is not a number times the same function, that is cos alpha x. So no, cos alpha x is not an eigenfunction of d by dx. Is cos alpha x an eigenfunction of d squared by dx squared? Well, d squared by dx squared operating on cos alpha x is equal to minus alpha times dx of sine alpha x, which is equal to minus alpha squared times cos alpha x. which is a number minus alpha squared times cos alpha x. So yes, cos alpha x is an eigenfunction of d squared by dx squared with eigenvalue minus alpha squared. The expectation value of an operator A with the function psi is defined as bra psi A psi ket, or in integral notation as integral psi star A operating on psi dx. Note that not every function is an eigenfunction of a given operator, but an expectation value can be computed for any operator with any function through the above relation. What is the expectation value of the operator d by dx with the function cos x in the interval 0 to 2 pi? The expectation value of d by dx is given by integral from 0 to 2 pi cos x complex conjugate times d by dx of cos x dx, which is equal to integral from 0 to 2 pi cos x times d by dx of cos x dx, since cos x is a real function. And this, upon performing the differentiation, gives minus integral 0 to 2 pi cos x times sin x dx, which is equal to minus a half integral from 0 to 2 pi sin 2x dx. Now let y is equal to 2x. So dy is equal to 2 dx, or dx is equal to half dy, and when x goes from 0 to 2 pi, y will go from 0 to 4 pi. So the integral becomes minus a quarter integral from 0 to 4 pi sin y dy, which is equal to a quarter times cos y from 0 to 4 pi, which is equal to a quarter cos 4 pi minus cos 0, which is equal to 0. What is the expectation value of d squared by dx squared with cos alpha x in some interval where the function is normalized? The expectation value of d squared by dx squared is given by integral cos alpha x star d squared by dx squared of cos alpha x dx, which is equal to minus alpha times cos alpha x star d by dx of sin alpha x dx, which is equal to minus alpha squared of integral cos alpha x star cos alpha x dx, which is equal to minus alpha squared, since the integral of cos alpha x star cos alpha x dx is equal to 1, since we have assumed that the function is normalized. Okay. Thus the expectation value of an eigenfunction of an operator is equal to the corresponding eigenvalue. So if a function is an eigenfunction, its expectation value will be equal to the eigenvalue. Okay. Now we define the concept of degeneracy. Two eigenfunctions psi and phi of an operator A are said to be degenerate if they have the same eigenvalue for that operator. That is, A operating on psi gives small a times the function psi, and A operating on phi gives small a times the function phi. Then psi and phi are said to be degenerate with the eigenvalue A, with the same eigenvalue A, this small a. Show that cos alpha x and sin alpha x are degenerate eigenfunctions of d squared by dx squared. To do this, we operate d squared by dx squared on cos alpha x, which gives minus alpha times d dx of sin alpha x, which is equal to minus alpha squared times cos alpha x. Operating with d squared by dx squared on sin alpha x gives alpha times d dx of cos alpha x, which is equal to minus alpha squared times sin alpha x. Therefore, cos alpha x and sin alpha x have the same eigenvalue minus alpha squared with the operator d squared by dx squared. Okay. In other words, cos alpha x and sin alpha x are degenerate eigenfunctions of the operator d squared by dx squared with the eigenvalue minus alpha squared. Okay. We now introduce the concept of commutative property. In general, Operator algebra is non-commutative. That means A, B is not equal to B, A. Okay? The order of operation of the two operators matters. If the two operators are such that AB is equal to BA, then A and B are said to commute. The commutator of two operators, A and B, written in terms of the square bracket A comma B, is defined as AB minus BA. Okay? The evidence for non-commuting operators in nature is the uncertainty principle. Okay? Do the operators x and d by dx commute? To evaluate this, we operate with the commutator upon a function psi. Thus, the commutator of x and d by dx operating on psi is equal to x times d by dx operating on psi minus d by dx operating on x psi, which is equal to x d psi by dx minus x d by dx operating on psi plus psi d by dx operating on x, where we have differentiated by parts in the second term. This gives x times d psi by dx minus x times d psi by dx minus psi times dx by dx. The first two terms cancel out and dx by dx is equal to 1, and therefore this gives minus psi. In other words, the commutator of x and d by dx operating on psi gives minus psi, or the commutator of x and d by dx can be said to be equal to minus 1, which is not equal to 0. So, no, the operators x and d by dx do not commute. Note that here x is the position operator and d by dx is related to the linear momentum operator. Do the operators d by dx and d squared by dx squared commute? The proceeding as before, we get commutator of d squared by dx squared and d by dx operating on psi is equal to d squared by dx squared times d by dx operating on psi minus d by dx times d squared by dx squared operating on psi, which is equal to d cubed psi by dx cubed minus d cubed psi by dx cubed, which is equal to 0. Therefore, the commutator of d squared by dx squared and d by dx is equal to 0. And so, yes, the operators d by dx and d squared by dx squared commute. So, note here that that d by dx is related to the linear momentum operator and d squared by dx squared is related to the kinetic energy operator. Okay. Note that the commutator of b and a is equal to minus the commutator of a and b. Okay. Since the commutator of b and a is equal to ba minus ab, which is equal to minus of ab minus ba, which is minus of the commutator of a and b. Thus, the commutator of d by dx and x is equal to minus the commutator of x and d by dx, which is equal to 1. The commutator of two commuting operators is 0. That is, if BA is equal to AB, then the commutator of B and A is equal to 0. An operator A is said to be Hermitian if and only if integral phi star A psi dx is equal to integral A phi complex conjugate times psi dx, where phi and psi are any two functions. Okay. In Dirac notation, we can write this in a simpler form as bra phi A psi ket is equal to bra A phi psi ket. Note that anything in the bra, we have to take the complex conjugate of it. Okay. We now introduce the 5 theorems of linear algebra that we mentioned, in terms of which we can derive the whole of non-relativistic quantum mechanics. The first theorem is that the eigenvalues of a Hermitian operator are real. Okay. To prove this, let A operating on psi ket gives be equal to small a times psi ket. From the Hermitian property, we get bra psi a psi ket is equal to bra a psi ket, which is equal to bra small a psi times psi ket. But remember, everything in the bra has to be complex conjugated, and a is just a number, so we can take it out of the integral or out of the brackets to give a star times bra psi ket. Okay. But the left hand side is just bra psi times small a psi ket, which is equal to small a times bra psi ket. Again, we can take a out of the bracket since a is just a number. So comparing these, we see that a times bra psi ket is equal to a star times bra psi ket, or a is equal to a star, or the eigenvalue a is real. Okay. Let's outline the same proof in integral notation. So we let a operating on psi be equal to small a times psi. From the Hermitian property, we see that integral psi star a psi dx is equal to integral a psi star times psi dx, which is equal to integral small a psi star times psi dx, which is equal to a star integral psi star psi dx. Left hand side is equal to psi star small a psi dx, which is equal to a times integral psi star psi dx, since a is just a number. And so equating these, we see that a is equal to a star, or the eigenvalue is real. The second theorem states that the eigenfunctions of a Hermitian operator with different eigenvalues are orthogonal. Okay. The corollary of this is that any eigenfunction is linearly dependent on all other orthogonal eigenfunctions. To prove this, let a operating on psi ket be equal to small a into psi ket, and a operating on phi ket is equal to b into phi ket, with a not equal to b. From the Hermitian property, we see that bra phi a psi ket is equal to bra a phi times psi ket, which is equal to bra b phi times psi ket, which is equal to b star times phi psi ket, which is equal to b times phi psi ket, b times bra phi psi ket from theorem 1, since the eigenvalue b has to be real. So the left hand side we see is equal to bra phi small a psi ket, which is equal to small a times bra phi psi ket. So equating these, we see that a minus b times bra phi psi ket is equal to 0, but we have said that a is not equal to b, therefore a minus b is not equal to 0, therefore bra phi psi ket has to be equal to 0, or in other words, phi and psi are orthogonal. Outlining the same proof in integral notation, let a psi equals small a psi and a phi equals small b phi, with a not equal to b. From the Hermitian property, we see that integral phi star a psi dx is equal to integral a phi whole star times psi dx, which is equal to integral b phi whole star times psi dx, which is equal to b star times integral phi star psi dx, which is equal to b times integral phi star psi dx, since the eigenvalue b has to be real from theorem 1. From the left hand side, we see that's equal to integral phi star times small a psi dx, which is equal to small a times integral phi star psi dx. Therefore, equating these, we see that a minus b times integral phi star psi dx is equal to 0, but a minus b is not equal to 0 since a is not equal to b, and therefore integral phi star psi dx is equal to 0, or phi and psi are orthogonal. The third theorem is that the eigenfunctions of a Hermitian operator form a complete set of functions which can be used to expand any other function with the same boundary conditions. Geometrically, the orthogonal eigenfunctions of a Hermitian operator can be thought of as the coordinate axes of a Hilbert space. This is one of the most important theorems for quantum chemistry. The fourth theorem is that linear combinations of degenerate eigenfunctions of an operator are themselves eigenfunctions with the same eigenvalue. The corollary is that linear combinations of eigenfunctions corresponding to different eigenvalues are not eigenfunctions of the operator. Okay. So the proof is, let phi and psi be eigenfunctions of the operator A with the same eigenvalue small a. So A operating on psi ket is equal to small a times psi ket, and A operating on phi ket is equal to small a times phi ket. Let chi equal to b times phi ket plus c times psi ket. Therefore, A operating on chi is equal to b times A operating on phi ket plus c times A operating on psi ket from the definition of a linear operator, which is equal to b times A times phi ket plus c times A times psi ket. We can take A common to write this as small a times b times phi ket plus c times psi ket, which is just small a times chi. Therefore, we see that A operating on chi gives small a times chi. So chi is an eigenfunction of the operator A with the same eigenvalue A. To prove the corollary, namely that linear eigenfunctions of non-degenerate eigenfunctions are not eigenfunctions of the operator, let psi and phi be eigenfunctions of the operator A with different eigenvalues. That is, A operating on psi ket is equal to small a times psi ket, and A operating on phi ket equals small b times phi ket. Let chi equals c phi ket plus e psi ket. Then A operating on chi is equal to c times A operating on phi ket plus e times A operating on psi ket from the linear property, which is equal to cb phi ket plus ea psi ket, which cannot be written in the form of some number times chi. So a linear combination of non-degenerate eigenfunctions is not an eigenfunction of the operator A. The fifth theorem states that if two operators commute, their eigenfunctions are simultaneously eigenfunctions of both operators. Okay. To prove this theorem, let A and B be two commuting operators, that is AB equals BA, with non-degenerate eigenfunctions psi and phi, that is A operating on psi equals small a times psi and B operating on phi equals small b times phi. Then AB operating on psi is equal to BA operating on psi using the commutative property, which is equal to B operating on small a times psi from the eigenvalue property, which is equal to small a times B operating on psi. Similarly, BA operating on phi is equal to AB operating on phi from the commutative property, which is equal to A operating on small b times phi from the eigenvalue property, which is equal to small b times A operating on phi. So if we look here, A operates on B psi to give small a times B psi. In other words, B psi is an eigenfunction of A with the same eigenvalue small a. Likewise, from the second equation, B operates on A phi to give small b times A phi. That means A phi is an eigenfunction of B with the same eigenvalue small b as phi itself. In other words, B psi is an eigenfunction of A with eigenvalue small a, and A phi is an eigenfunction of B with eigenvalue small b. Therefore, by using the earlier theorem, since the eigenfunctions are non-degenerate, the the eigenfunction b psi has to be the same or just a multiple of psi. That means p psi equal to some number c times psi, and a phi has to be the same as phi or some multiple of phi, or a phi is equal to some number e times phi. So psi is also an eigenfunction of b, and phi is also an eigenfunction of a. That means the a and b have common eigenfunctions. We will stop here, and next time we will show that with the help of these 5 theorems we can derive almost all of non-relativistic quantum mechanics using the postulates of quantum mechanics, and we shall also show the origins of quantization.